Hi everyone, my name is Hao Wang. Today I will present a time series project named US CPI analysis. A CPI is a statistical estimate constructed using the prices of a sample of representative items whose prices are collected periodically. The annual percentage change in a CPI is used as a measure of inflation. An increase in CPI means that a household has to spend more dollars to maintain the same standard of living. In this project, we are going to analyze the US CPI data to understand if there is any trend from the history data and focus its future short-term and long-term values. The dataset to be used in this project is from US Bureau of Labor Statistics. It's all urban consumers CPI monthly data from January 2011 to February 2021. There are 122 observations without any missing values. The realization of CPI data looks not wandering. Clearly, there is a rising trend which indicates a violation to the first condition of constant mean for a stationary time series, although the variance of the data seems constant. The autocorrelation plot is slowly damping from 1, which also suggests a non-stationary time series. The spectral densities have one peak at f equal to 0. There is no evidence suggesting that there is seasonal trend in this data. As earlier mentioned, the realization of the data suggests a non-stationary time series. I will start the analysis from a stationary model. The first model we built is AR3. AIC5 function is used to check AIC and BIC. Both favor AR3. Then we estimate the fees, residual variance, and build the first AR3 model. We define the short term as 5 months and long term as 20 months. Then we did the cross validation. Short term AIC is 2.24, comparing to the rolling windows AIC 2.92. Long term AIC is 11.12, comparing to the rolling windows AIC 17.54. This result indicates a better focus on short-term than long-term period. The second model we built is ARIMA 212. A non-stationary factor 1 minus b is added in the model. So we got the final model showed in this slide. The cross-validation short-term AICE 6.02, rolling windows AICE 4.26, long-term AICE 21.01, rolling windows AICE 20.56. Seems that ARIMA 212 model has worse focus comparing to that of AR3 from ASE perspective. Next, we fit a multivariate regression model using both trend term T and the employment data. As you can see in the plots, both short-term and long-term prediction take the trend term into account. The residual of this regression model can be fit as an AR3 model. We use AIC5 to check this AR3 model. Both AIC and BIC options favor P equals 0, Q equals 0, which means that the AR3 model explains the residual data very well. The variance of the AR3 model is suggesting a white noise. Looking at the cross-validation, short-term AICE 0.54, rolling window AICE 3.33, long-term AICE 1.56, rolling windows AICE 20.64. Next, we fit a model using VAR method. Again, both trend term and employment data are used as explanatory variables. The VAR selection favors the lag 1 from both AIC and BIC perspective. We fit the regression model using lag 1 of each variable. The estimated coefficients for equation y1, which is CPI, is given in this slide. The cross-validation, short-term ASE 1.06, long-term ASE 3.48. Next, we use the MLP function to fit a neural network model. There are 2 inputs in this model and 1 hidden layer with 5 hidden nodes. The cross-validation of this model, short-term ASE 0.755, long-term ASE 1.13. Lastly, we come out an ensemble model using the average prediction from one model and the neural network model as the prediction of this ensemble model. The cross-validation, short-term ASE 0.51, long-term ASE 1.88. Finally, we have all the cross-validation results from the 6 models we introduced previously, summarized here in this slide. We found that ensemble model gives the best short-term prediction with the lowest short-term ASE value of 0.51. And the neural network model gives the best long-term prediction with the lowest long-term ASE value of 1.13. Thank you for watching this video.